Hello, I'm Pablo, and I will be doing the first half of this presentation. Then Alex will be doing the second half. So, without cryptocurrencies, if you want to make a transfer through the internet, you need an intermediary, like a bank. And a bank just basically has a ledger with the amount of money that you have in your account. And when you do the transfer, you have to tell the bank, okay, now I have less money, and the recipient of the transfer has more money. And what cryptocurrencies do is they just distribute the ledger so that everybody has a copy of the ledger. And with that, we can essentially overcome the need to trust a third party, to trust the bank. But this is not always enough. Sometimes you need to do other things, like, for example, exchange an amount of money in one currency for an amount of a different currency. And you cannot just do two transferences, because then you need to, one of the two parties has to trust the other party to do their bit. Whoever goes second will not just keep both of the parts, right? And that's what smart contracts are for. Smart contracts are basically like normal contracts, but they are written in the distributed ledger. And instead of being written natural language, they are written in a programming language. They are essentially computer programs, and they are not interpreted by a judge. They are interpreted by a computer. They are not enforced by law. They have to be self-enforcing. For example, a smart contract cannot force you to do something or to pay something, which is a limitation. But if you do transfer an amount of money to a contract, or for example, a token, then the contract can decide what to do with it. So it's self-enforcing in that way. The other thing is, because there is no judge, if you make an error when writing a smart contract, then there's no one that will interpret the original intention of that contract. The error will modify the contract, and that will be the consequences of the contract. So, for example, it can be that the money will end up going to the wrong hands, or even it can happen that the money will be destroyed forever. So that's quite bad. Also, so what do we do about this? The Marlowe language is a domain-specific language which is aimed specifically at writing smart contracts in top of cryptocurrencies. And it is very, very simple. So if you know Haskell, you actually can generate Marlowe smart contracts very easily, because Marlowe semantics are defined as a Haskell data type, which you can see in this slide. And the syntax and the semantics are defined as a function, a set of functions in Haskell. So it is very, very straightforward. In addition to that, so why do you want to use Marlowe instead of general purpose languages? And the reason is that general purpose languages give you more flexibility than you probably need for making day-to-day transactions or to making smart contracts. And with these possibilities, it also comes the opportunities to introduce bugs in the contracts. So Marlowe is good already because it reduces the number of possibilities, and it's also good because it is designed to be easy to read, to be clear, to be explicit, and to avoid most of the pitfalls that you can make, well, the most common pitfalls that you can make while writing smart contracts. Like, for example, forgetting to give a timeout for parties to do things. For example, for making a deposit. So if you don't give a timeout to a party, the party can decide to stall the contract, which can be can translate in a problem for the other parties. It can be leverage, and you can also forget, for example, to refund money if there is the contract is aborted, right? And all of this is enforced by Marlowe. Also, because it is limited in scope, we are able to actually statically analyze Marlowe contracts automatically. So you can say, for example, you can make sure that if a Marlowe contract says that it's going to pay an amount of money, we can statically analyze whether at that point in the execution of the contract, there will be for sure enough money to make that payment. So we can ensure that Marlowe contracts keep their promises, right? And also we have developed an IDE, a web IDE, which we call the Marlowe Playground, which is what this presentation is about. And this Marlowe Playground allows you to create, to edit, to simulate, to analyze contracts. And both Alex and I will be using the Marlowe Playground from now on in order to demonstrate how Marlowe works, how to create Marlowe contracts, and of course, how the Marlowe Playground works. So give me a second to share my screen. Okay, this is the Marlowe Playground. We can see we have 6 main tabs. The 5 first tabs correspond to 5 different ways of editing Marlowe contracts, and the last tab corresponds to a way of seeing how the Marlowe contracts will behave once they are deployed in the blockchain. The main tab is the simulator. The simulator shows the Marlowe contract as it is, as text. You can find, not only in the simulator, also in the other tabs, you can find there are examples up here. You can click in order to load, to try them. And the simulator, in addition to this, has on the right side a way of controlling the contract, so seeing what happens in a kind of omniscient way, because you can see what every party can do. And you can also travel in time by moving this to a future slot. On the bottom of the simulator, you have this pop-up which also shows you the current state of execution. It provides you with the static analysis tool, and it also shows you the warnings and the linting problems, the errors during execution, and it will log whatever happens during execution. You can also find these small blue icons here. If you click them, you can get contextual help here as well, for example. Additionally, it's worth noting that you can find the tutorial here. If you want to find more information about the playground or about Marlowe itself, this tutorial has a lot of extra information you can check. Other ways of editing and creating Marlowe contracts are using the JavaScript editor, which allows you to write contracts using JavaScript and TypeScript as well. You can use the Haskell editor to use Haskell. As we said, Marlowe is a Haskell data type, so it's very straightforward to create Marlowe contracts using Haskell. You can use Blockly, which we will see in a minute. And you can also use the labs, which is currently under development, but you can use it to instantiate templates of financial products like Principle of Maturity. Finally, you can use the wallet to simulate the execution of contracts in a way which is more like what you will see when the contract is deployed in the blockchain. So you can see what each of the parties sees and how they can interact with the contract. But let's start with Blockly. I think Blockly is the most beginner-friendly way of creating and editing Marlowe contracts, because it gives you all the blocks you need to create Marlowe contracts in the shape of jigsaw puzzle pieces. Contracts are the main construct of Marlowe contracts. Let's do the swap contract that we mentioned in the slides, the contract that will allow Alice to exchange ADA for dollars with Bob. So the first thing we want to do is to ask Alice to deposit ADA to the contract. We can do that by using when. All the contract constructs are executed immediately except for when. When is the one that's used to wait for a participant to do something. The first gap represents the thing that we are waiting for, or things. The after slot number means until when are we going to wait. And the second gap represents what we are going to do if the thing that we are waiting for doesn't happen by the slot number we write here. So let's use close in this gap. Close, what it does is terminates the contract, and it will refund all the money in the accounts of the contract to the owner of each of the accounts. So that's a nice way of finishing. What we want to wait is an action. In this case, a deposit. here are the pieces of information we need to know about for a deposit. First, we want to know who makes the deposit. In this case, would be Alice. And we can represent parties by using the party construct. We have two ways of doing that: the roles and the public keys. The difference between roles and public keys is that public keys cannot be transferred, because you can only prove that you own a public key by using a private key, and you cannot just tell someone that you will forget the private key. They will have no way of knowing that you have forgotten the private key. So you cannot lose the power over a public key. But you can transfer a role in the same way that you can transfer a cryptocurrency. So let's use roles. So this role is going to be called Alice, and she's going to deposit 12,065 ADA, which we can specify by using the constant here. I'm writing 12,065. Now we have to specify the currency, which as we know is ADA. Currencies are specified using the token construct. Here we can specify generic token, which we'll use later, but we specify ADA. And here we specify the account in which we want to deposit, which would be the account number 1, owned by Alice. Now let's do the same thing again for Bob. So I just copied this using Ctrl+C and Ctrl+V. And now we can replace Alice with Bob. The account also belongs to Bob. And here we are going to say 1,000, and we are going to say $. I'm going to remove this using delete. And we are going to use the token here constructor. This token constructor, here we should put the hash represented as an hexadecimal code, the hash of the currency token, and here we write the name of the token. So let's leave the hash blank and let's write $. Instead. And let's increase the timeout to allow an extra 10 slots for Bob to deposit. Okay, once we have deposited all the money, we can make the payments. So for that, we use the payment construct here. And first we need to specify who receives the payment. Here we use the payee construct. We could deposit it, we could transfer it to another account, but in this case we want to pay directly to, let's say, Alice in the beginning. Then the amount will be the one that Bob deposited. The currency will be the one that Bob deposited, and the account owner will be Bob again. And now we do the same thing for Bob. We write Bob as a payee. The amount of money will be the one that Alice deposited. The currency will be ADA, and the account will belong to Alice. And since we have already done the swap, we can finish the contract by using the construct close, which will do nothing in this case. Once we are happy with our Blockly contract, we can transform it into an actual Marlowe contract by using the button Send to Simulator. And here we are back in the simulator. We can see that in the right side now, the option is the one we provided at the beginning. 12,065 ADA are to be deposited by Alice into the account that's one that she owns. So if we take this action, you can look at this contract while I click the action. We can see that the top of the contract disappeared now because we no longer expect Alice to deposit. We can see that now the account that belongs to Alice has 12,065 ADA, and we can see the deposit in the log. So let's keep going. Now Bob deposits $1,000, and we can see that the contract has been closed already because the moment Bob deposited the $1,000, all money was the ADA was paid to Bob, and the ADA was paid, and the dollars were paid to Alice. This is what I meant that all contracts execute immediately. One was waiting for us to do something, but the pay happened immediately. Okay, so let's reset the contract to go back. And now let me show you another cool feature of the Marlowe Playground. You may have wondered when we were doing the contract in Blockly, how do we know which type of block? Because we have 8 types of blocks. So if you are a beginner, you may not know that here you need a party block or an account block. So what you can do to find out is you can just leave the gap blank, like here, right? And if we click send to simulator, we can see that instead of the normal Marlowe, the place where the gap was, the hole was, we get this string with a question mark. This is called a hole, and if we hover over the hole, we'll get this tip, and if we click in quick fix, we will get 2 suggestions of the possibilities that we can put here instead of the hole. We had done party, and we can see again we get another hole which we can hover over, and then we can click row, and it will fill the string with a default thing which we can replace with Alice. So you can also go from here to Blockly by using this button. And you can change between Blockly and holes, and you can use whatever is more convenient at each moment in the creation or edition of Marlowe contracts. Okay, so now let's make this contract a bit more complicated in order to illustrate some more of the construct that Marlowe has. For that, we are going to change this constant and allow Alice and Bob at runtime to decide how much money they want to exchange. So let's set this aside, and let's now use another type of action for which we need a when construct first. Let's say we wait until slot 10, and if not, as usual, we will close the contract. This time the action is of type choice. Will allow Alice to choose how much money to exchange. And we are going to call this choice Alice choice. Of course, the owner of the choice is going to be Alice, who is the one that makes the choice. And here we write the options that Alice has to choose from. So we use the bounds. And here we say Alice can choose between $100 and $10,000. And now we can do the same thing for Bob, so that we give both a choice. Bob choice. Now it belongs to Bob. And now at this point, let's put here 20, so we have extra time for Bob. At this point, we have the choices. We want to find the minimum amount that both are agreed to exchange. And for that, we'll store this value using the let construct, which will give a name to that value. So we can call that amount of dollars. And we can refer to the choices by using values. Like we used constant before, we can use choice. We can fill it with the choice name and the owner of the choice. And we can do the same for Bob. Now, in order to get the minimum amount, we'll pick the one that's the smallest. So we can use this if construct of the type value. If the value of Alice is smaller, we will choose Alice. If not, we will choose Bob. So in order to know which one is the smallest, we use the observation value is less than. So if the choice by Alice is smaller than the choice by Bob, then Alice, otherwise Bob. And we can put this into the variable amount of dollars using the let construct. But we also need to know how much ADA we want to transfer, and we can do that by using a conversion rate. So let's make another let construct and call it amount of Ada, and in order to use the values defined by let, instead of using choice, we use and we use the name of the let. We can do the same for the amount of Ada that we are going to define. Let's put this here. In order to calculate the amount of Ada, we use scale, which basically multiplies by a fraction. So this fraction represents the conversion rate, which in our case is going to be 15,081 divided by 1,250. Let's get this out again. So now we have defined both the amount of dollars and the amount of Ada. So we can go ahead and replace it in here. This is the amount of Ada. This is the amount of dollar. This is the amount of dollar. And this is the amount of Ada. Now we can go back and join the subcontract. And now we are done. We can go back to the simulator and see how this works. So we can see that now, first Alice is asked to make a choice. In this case, we can say Alice wants to exchange, for example, $500. Now let's say 5,000. We can see that Alice made the choice. Now Bob is asked for a choice. Let's say that Bob only wants to exchange $1,000. And now Alice is asked to deposit 12,065 Ada, and Bob is asked to deposit $1,000. And then the exchange goes as expected. And that's all for me. Now, Alex will show you other ways of editing Marlowe contracts and also how to use static analysis to ensure that your contracts are correct.
Hi, I'm Alex from Marlowe team at IOHK. Let's check out some other cool features of Marlowe Playground, such as hole-driven development, static analysis, Haskell editor, and JavaScript editor. Marlowe is a non-Turing complete language. That means that all contracts terminate at some point, and we know the maximum time a contract can execute beforehand. Hence, it's impossible to lock money forever in a contract. For example, in the contract Pablo has created, the expiration time is 40, and we can see this is a maximum timeout we're waiting for in a contract. The beauty of Marlowe design is that it's possible to analyze contracts statically using SMT solvers. SMT solvers are a class of software that can solve equations in symbolic form. We represent a Marlowe contract as an equation and ask the solver if it could find a sequence of user inputs that would lead to a partial or failed payment due to lack of money in participant's account or invalid user input. This helps to develop contracts that are guaranteed to execute payments regardless of participants' behavior. Suppose we made a mistake and asked Bob to pay amount of Ada of dollars to Alice instead of amount of dollars. In this case, amount of Ada would be much larger than amount of dollars in Bob's account. This is a very easy to make mistake. If we analyze such a contract, SMT solver would be able to find the list of transactions. That would lead to a partial payment. The contract is supposed to make a payment of 1,500,000 units of dollars from account 1 of Bob to Alice, but there was only 100. And you can see the list of actions that needs to happen for this error to appear. So Alice needs to make a choice 100, Bob needs to choose 101, for example. They have to do their deposit transactions, and the error gonna appear. Let me show you another cool feature of Marlowe Playground. We can create contracts using holes and quick fix feature of the editor. Holes are these identifiers with a question mark in front of them. If you press on this light bulb, it shows you basically what can you do in this place in the contract. Let's construct a simple trust fund contract. Alice deposits money into a contract in a way her son Robert can obtain the money at maturity date. However, the contract allows Alice to get her money back before the maturity date if she changes her mind. For that, first we need a deposit from Alice. We start with when. Suppose we expect Alice to deposit her money before slot 3. Otherwise, we just close the contract. Here we expect a case and action would be deposit. We can format our document to make it more readable. We expect a deposit from role Alice into account owned by Alice from Alice. Token would be default token, which is 8am, and the value would be 1 million. We need to allow Alice to change her mind. For that, we expect an input before maturity date. So we allow her to make case action choice. Let's call it refund. Only Alice is allowed to make this choice, and all user inputs in Marlowe are bounded. In our case, we need single value. That's enough. That would mean that Alice decided to refund. Bounds are inclusive, so this bound means only 0 is a valid input. So in case Alice decided to change her mind and refund, we simply close the contract, and money deposited into Alice's account will be refunded to Alice. We wait until the maturity date. Let's say it's going to be 10. Otherwise, we pay money to Bob. Pay account from Alice, of course, to party Bob. Format. Token would be again 8am. Value, let's copy paste 1 million, and then we just simply close. If we analyze this contract, we'll see that there is a partial payment. It's a wrong contract. The contract is supposed to make payment of 10 million units of ADA from Alice to Bob, but there is only 1 million. That's because I made a mistake. And our editor shows you this immediately. So you can see this a contract is highlighted because there is a warning. In order to avoid such mistakes, you can use a special construct that's called available money. This construct evaluates to all the available money in a particular account. In Alice's account of ADA tokens. If we analyze this contract, it says that no warnings were found. Let's try to execute this contract in Marlowe Playground. Our simulator analyzes the contract and shows all the available actions possible to do in a particular contract in a particular state. Currently, all the possible actions is either for Alice to deposit 1 million units or just do nothing and wait for slot 3. 3 is our closest timeout. In this case, if we just do nothing and wait until slot 3, we just press this plus button and see that contracts evaluates to close, nothing happens, current slot 3, logs show no activity, nothing happened. We can reset our contract execution and we return back to the whole contract, and we can try another input. So other input is for Alice to actually deposit 1 million units. Also, disclaimer, I say units of ADA because smallest unit of ADA is actually Lovelace. So 1 million units of ADA is actually 1 million Lovelaces, and this is 1 ADA. So if we deposit, we see that contract reduces to its continuation. We see in logs that actually Alice deposited 1 million units of ADA. And we see current state that Alice's account 0, contains 1 million units. Next, our available actions are actually for Alice either to refund before a maturity date or just wait for maturity date to happen. So you see that we show move to slot 10, which is our next interesting slot because it's a maturity date timeout. But we actually can move contract forward in time to whatever slot we like. Let's say 4. Nothing really happens, but we can see that current slot in this simulator is 4, but nothing changed much. If we wait for maturity date, we see that contract is closed, and in logs we see 2 actions. First initial deposit, and then contract pays 1 million to Bob. That's the happy execution for Bob. We can undo one action, and for example, Bob didn't behave well, and Alice decided to leave him without money, so she decided to refund. So she just make a choice of a refund, and we see that Alice made a choice, and contract pays 1 million back to Alice, which is a refund. Many common mistakes are immediately shown in the simulator editor, just syntax errors or simple mistakes like choices. All the choices are bounded, so you just cannot enter anything wrong outside of bounds and cannot use this input. Also, if you try to use wrong account, you'll get warnings like this saying that there's a payment before deposit. All this is great, but what if making trust funds is your business and you would like to create a bunch of contracts with different role names and different amounts to pay and different maturity dates, and you want to parameterize in all these values. For this, you can use a JavaScript editor or Haskell editor to create contracts that you can parameterize. Let me show you an example. In Haskell Editor tab, we have a single Haskell file editor, and when this file is compiled, it's expected to just print a Marlowe contract. And whatever it prints, we can then simulate and execute. So if I just copy-paste our previous example, our trust fund, I can just compile it. This file gets compiled on our servers and then executed, and it just prints out the Marlowe contract. We can see it. That's basically the same contract we had before. We can just send it to simulator and work with it. But we can use many Haskell features to customize our contract. For example, we can parameterize it with, say, amount of money to be paid. So I just create a parameter and make this contract a function that gets amount as a parameter. And for example, maturity date. Maturity date is another parameter of this function. So maturity date will be here. So now contract becomes a function, and if we apply arguments to it, say 5 million, and maturity date, say slot 15. So when we compile it and run, we get another instance of a trust fund. We can see it here, and we can send it to simulator and see it's 5 million and maturity date is 15. We can deposit, wait for timeout, and see that Bob got 5 million from Alice. Another fun, although experimental feature in Marlowe Playground is our JavaScript editor. It's just a JavaScript file that allows you to generate Marlowe constructs using our small JavaScript library. Let's see an example of simple zero coupon bond, where investor can buy a bond with discount without coupon. So you can see that we have a when construct. We expect a deposit from investor of 850 ADA, and then we paid to issuer, and then we expect an issuer to deposit 1,000 full notional, and then we pay it back to investor. Very simple contract. And again, we can parameterize this contract using just normal JavaScript or TypeScript, in this case, functions. So let's parameterize on a notional and a discount. Function zero coupon bond, full notional and discount, and we just return our contract and use notional here, and let's calculate discounted value as a notional minus discount and use it here and here. And when we call this function, we can use IntelliSense. It's gonna say what it expects, 1,000 and discount 150. Say when we compile it, we get the well, basically the same contract. We can send it to simulator, and you see that investor is expected to deposit 850, And then issuer expected to deposit 1,000, and the bond is completed. You can use whatever JavaScript you like here, which is sort of cool. Thank you for watching, and I hope you'll enjoy playing in our Marlowe Playground. Thank you.
Here well, first of all, we would like to answer any questions you may have. The platform we have prepared for receiving the questions from you is the one in the VR environment that you can find in the Learn Bright. So if you want to ask any questions, you can make it to the room, Laramie room. In the meanwhile, we can introduce some of the plans we have for Marlowe in the future. So we are currently working in a complete UX redesign of Marlowe, which will be more focused instead of having so many tabs. And we also very excited because it's getting close to the time we can deploy Marlowe contracts in the Cardano blockchain. Right now, we can already execute them offline, but and Marlowe is implemented as a Bluetooth contract, but we cannot yet use them in practice. And also, we will be developing new systems for statically analyzing Marlowe contracts. You can already see the most recent addition was the reachability analysis that lets you know if some parts of the contract are impossible to reach, because that will usually show you things you didn't expect about the contract. And there is also a lot of work going on about Actus, about the lab tab that Alex just showed. Actus, Santiago Norena just asked you, what is the Actus? Actus is, maybe Alex can explain it better.
Hi, do you hear me?
Yes.
So Actus is a standard of financial instruments developed by several guys from Switzerland who used to work with banks and financial industry for quite a while, and they realized that many of those instruments have unclear semantics. So the idea was to specify semantics of financial instruments precisely with the specifications. And Actus is a standard that describes financial instruments in a mathematical way with formulas and precise semantics. And we're working to implement this specification using Marlowe and Haskell. We have a Dmitro Kondratyuk from IOHK who is working on this task, basically. So we have implemented principal and maturity contracts and several others. So if you're familiar with financial instruments, that would be easy for you to use our library to instantiate financial contracts that are used in banking and in finance.
Indeed, I would just like to add that later at 11 a.m. Wyoming time, Niels and Dimitri will be talking about Actus in that we will have a presentation. So if you want to learn more about Actus, definitely go to this presentation. And another talk, the talk just after this talk in this room exactly, it talks about Bluetooth, which is a language, which is a general purpose language. So if you want to do things which are too complex for expressing in Marlowe, then you will be able to use this language. So you can learn more about that in this presentation.
Yes, we actually use Bluetooth to implement Marlowe.
Mm. And I don't know much more to say. So right now there doesn't seem to be a lot of people in the virtual reality room. Thank you. Um, so if we don't have any questions, maybe we will leave it there. What do you think, Alex? Would you like to add anything?
Well, let's wait for a minute or two for another questions, and meanwhile we can briefly talk about our plans, what we are about to accomplish next. So Pablo told you that we have plans to extend our static analysis tools, and it's just a lot of things we can do with Marlowe because of its non-Turing complete. We can analyze many interesting and check many interesting properties. Reachability analysis, and we can enhance static analysis further. We have, I showed you the JavaScript implementation. We will work on that as well, so you could generate Marlowe contracts using JavaScript, which should allow larger amount of developers to actually use Marlowe. And for like future plans, we're thinking about implementing Marlowe on top of Ethereum. So it's possible, and you could write Marlowe contracts that would work on both blockchains, and actually on Ethereum Classic as well, if you're interested. So on 3 chains, which is kind of cool.
Santiago Norena just asked the question, what are cool features do you recommend to add for the hackathon? So I think, so that's the goal of the hackathon, as I understand. So we would like you to come up with good ideas in ways we can improve. I think it's related to Actors in particular. Is that right?
Yeah. There is a set of challenges for extending access that Simon prepared. So yeah, you can read it, but I don't know where exactly, but it should be posted somewhere. Another point would be that if you would like to write smart contracts on Cardano platform, the primary option for you to use Plutus programming language, which is essentially it's a Haskell that gets compiled into our special Plutus core. That's actually what executed on chain. But that's a general purpose language with, and you have to be quite involved to do things there. So if you have a relatively simple contract in mind, using Marlowe would be ideal. Basically, you can see that in Marlowe Playground you can simulate it, try different things, analyze it, see warnings, errors, and we're gonna implement just basically one button to actually deploy the contract to the chain eventually. So that would be, I think, the easiest way to interact with smart contracts on Cardano.
Indeed, if Marlowe is enough for what you want to do, I think it is much easier it's easier than Bluetooth. It will be harder to make mistakes because it has some warranties. So some of the warranties that we've checked using automated theorem improvers about Marlowe is, for example, that the money is always preserved. So you cannot destroy money. It will, everything that goes into the contract will eventually go out after the timeout. And we have also a limited number of inputs for any contract. You cannot overflow the contract because for any given contract there is a number of things you can do, and you can only do those things.
Mm-hmm. Yeah. Another thing is that Marlowe seems very simple and somewhat limited. That's actually true. That's their plus and minus in the same time. But if for some reason you find that Marlowe is not enough to complete your particular task, we're preparing an extension for Marlowe called foreign function interface. So you can call Bluetooth functions, like arbitrary Bluetooth functions you can write to do more complex stuff, and then use results of these computations inside Marlowe. So we will provide a way to extend, like standard way to extend Marlowe.
Yes, very good point. I had forgotten about that. Yes, that's in the pipeline as well.
Yeah.
Santiago Norena asked, is there a way to create export contracts created in Marlowe to Bluetooth? I'm confused about export contracts. I'm not sure what you mean. Did you?
Essentially, on Cardano, like every Marlowe contract is a Bluetooth contract. So we implemented Marlowe as an interpreter in Bluetooth. So basically, if I understand what you're asking correctly,
to export contracts to Bluetooth, yes.
Yeah, so every Marlowe contract is a contract in Bluetooth. That depends on how what result would you like to get, because essentially Marlowe interpreter written in Bluetooth and contracts are written in like sort of Bluetooth. So you can say that you can create and export Marlowe contracts to Bluetooth, yes, because you have a source code of an interpreter and the source code of the contract you developed. So yes, you can.
We did discuss a bit about compiling Marlowe to Bluetooth, and we haven't explored that yet, but it may be that it's actually you end up with bigger contracts than just by using the Marlowe interpreter of Bluetooth. But it's something we had planned to research as well.
Mm-hmm. Currently, it's much simpler to have an interpreter because it corresponds to the semantics we have expressed in Haskell. It's like 1-to-1, like 99% the same, just like a couple of lines we extend to be able to run it on Bluetooth. So it's when we extend language with new features, it's much simpler to extend the semantics and interpreter. It's basically the same code. If you have a compiler to Bluetooth, you'll have more places to introduce the change and then to check that it actually it's the same. It corresponds to semantics, which is much harder to do with compiler than with interpreter.
Yes, so Leonardo says, just thought it would be useful for managers to create specifications here and then export that for developers in Bluetooth. That's an interesting idea. Haven't thought about that possibility, maybe.
Well, if managers or analysts created a contract, a Marlowe contract, they could just give them to Plutus developers, and that I think would be enough, because just Plutus developers could use this contract and feed it into Plutus implementation of Marlowe interpreter. So that actually should work. One last question from Santiago. Can I export any JavaScript visualization libraries to use with the JS editor? No, not now, but that's interesting. Currently, we have a predefined JavaScript libraries we use, and others can use in Marlowe Playground, but I think we can extend it with some visualization libraries later. No, don't be sorry for questions. We're here to answer those, so you're very welcome to ask.
Indeed, thank you very much for the questions. Thank you for attending the presentation.
Thank you very much.
Yes.
Yeah.
Yes, we're running out of time. Thank you very much.